Hey, this is Leach with Simpson Math, and today we are continuing our discussion about sampling distributions and specifically the Central Limit Theorem. So to do this, let's look at our Dr. Pepper examples again. So just a reminder, it says manufacturers of products have to make sure that they at least meet their advertised claim, including their claims of weight and volume. So suppose for a 12 fluid ounce can of Dr. Pepper that the Temple Bottling Company actually has a goal of filling all cans to 12.07 fluid ounces on average, which would be the mean, and a standard deviation of 0.04 fluid ounces. So this is a single can. Now we've looked at this before. So if you recall from a previous lecture, we answered the question, what percent of cans are underfilled? We defined X to be the volume of Dr. Pepper in an advertised 12 fluid ounce can. And we use this model where it's normally distributed with the mean of 12.07 and standard deviation of 0.04. And we said what percent of cans are underfilled. So that would be with our picture here, we have our mean at 12.07, standard deviation of 0.04. We go to where 12.0 is, and we find the area less than that, and that ended up being at about 4.01%. Now, to be clear, according to this model, just difference between what's previous and what's here. If we select a single, which you just realized I misspelled single, I spelled it signal, a single can at random from the population of all 12 fluid ounces of Dr. Pepper cans, there is just over 4% chance, 4.01% chance of getting a Dr. Pepper that is underfilled. Now, that's one single can. We're going to change this just slightly. So now we're going to look at some probabilities where we buy two 8-packs. Yes, 8-packs do exist. So we're going to buy two 8-packs. So that's a total of 16 cans. And we're going to find the averages of volume. We're going to find the average volume of Dr. Pepper cans. So let's do that. So first, what in the world is X bar? Well, X bar is the mean volume of Dr. Pepper in 16 cans. So make sure to always mention the sample size whenever you're defining X bar, because sample size does play a role with the distributions of these sampling distributions. All right, so let's talk about our shape here, or this model here. So this is X bar, so notice we have the bar on top of that X. It's not just this X, like here, it is now X bar. So first up, what's this shape of the sampling distribution going to be? Well, since the distribution of cans is normally distributed, when I'm just grabbing one, if I'm grabbing and averaging 16 of them, it will also be normally distributed. So we can just put our capital in there. If it's skewed, then our sample size should be at least 30 to be safe, but sometimes you can get away with a little bit smaller sample size, as you might see as you work through this chapter. But our default value for big enough is 30. But it's already normal, so we don't have to worry about sample size. All right, where's our mean going to be? Well, the mean is going to be the same mean that we had before, 12.07. And then that's because the mean of the sampling distribution of sample means is equal to the mean of the population. All right, lastly, for the standard deviation, if you recall from last lecture, it's our standard deviation of the population divided by the square root of the sample size. So sigma of X bar, the standard deviation of the sampling distribution of sample means, is the standard deviation of my population, so just X, divided by square root of n. So here I can just say that this is 0.04 over square root of 16. Now, I can go ahead and simplify this just for my sanity and say that this is 0.04 over square root of 16, and that's a nice perfect square. So 0.04 divided by 4, which we end up with as being 0.01. On your tests or labs and assignments and stuff that you do, when I ask you for the distribution, I would like for you to give me the full math for the standard deviation, and then you can approximate it. Here, this actually gives us an exact answer, but I chose two 8-packs instead of two 12-packs because 16 is a perfect square, so I knew that our math would be nice for this example. But if it was two 12-packs, and you'd have to divide by square root of 24, and then this would definitely be a gross, messy, approximated decimal number. So then that's why it's better for you to just leave it in this exact form. All right, so we're allowed, and just to answer why are we allowed to say this is true, that's because the population itself is normal, so that means that this shape is normal, and then based on these other facts about these formulas. All right, so what is the probability that x bar is less than 12 fluid ounces? So to be clear, this is saying that what's the probability that you grab two random 8-packs, which essentially is you grabbing 16 random cans of Dr. Pepper, and then you figure out how much total Dr. Pepper there is. You divide it across the 16 cans, so you find the average. What's the probability that this average will be less than 12 ounces? All right, so I have my model this time, still centered at 12.07, but this time my standard deviation is 0.01. Now with this 0.01, that's quite a bit smaller. So my 12 ounces as well, that's 12.06, 05, 04, 03, 02, 01, 12.0, way over here. So whatever this area is less than that 12. Now what we know about the normal model, if I'm at 3 standard deviations below the mean, the area less than that is about 0.15. So what about the area way over here? Probably basically 0. But we have technology at our disposal, so let's go ahead and figure that out. So let's go to Desmos, press Functions, go to Distributions, pick Normal Distribution, type in our mean at 12.07, comma, our standard deviation, and I'll go ahead and do the full math, 0.04 over the square root of 16. All right, we want to let me zoom in on that graph. Just for fun, I'm going to change this to red. There we go. And let's find our cumulative probability. So from negative infinity all the way up to 12. Now, 12 is like way over here on the graph. So if you compare where 12 and the graph is, not much is happening. And in fact, as you can see right here, that this is 1.2798 blah, 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 times 10 to the negative 12. So that's 0.00000. So 11 zeros. Okay, if I was to write out 11 zeros, okay, board, and then 1 point, not 1 point, but 1.278798. So it's pretty small, basically almost 0. So we're going to say that this is approximately 0. So the probability that x bar is less than 12 is approximately 0. We can be a little bit more exact and say that's at 1.2. I was going to round up to 8 times 10 to the negative 12th. So I want you to notice the differences between these two. One, just visually, one has a bar, the other one doesn't. So that's a tiny little difference. But notice conceptually what's happening, how they're actually pretty significantly different. One is a single can, and the variability within that single can is a 0.04 standard deviation. But when I'm looking at the average of 16, my standard deviation has dropped down to 0.01, 4 times as small. So the likelihood that I get a number as far away as 12, or basically 7 standard deviations, is pretty rare. Not impossible, but pretty rare. So it's not very likely that you would get that underfilled. All right, so let's talk about how surprising that is. In statistics, we often consider things being unusual when they happen less than 5% of the time. This 5% is a pretty important number within statistics. While it is possible for an unusual event to occur when it does, it often gives us reason to pause for a moment and evaluate if this is likely one of those times when this happens just by luck, maybe good luck, maybe bad luck, just depending on the situation, or it is likely that our model, distribution, expectations, our assumptions, all the things that we built, maybe they're not correct. In the coming lectures, we'll be looking at this idea a little bit closer. But for now, let's just make a note whether it's unusual. So it's unusual if it occurs less than 5% of the time. Additionally, this 5% threshold is around 1.645 standard deviations from the mean when you're using the normal distribution. So is it unusual to have a mean of 16 12 fluid ounce cans be underfilled? The mean of all of those? Yes. Because the probability of x bar being less than 12 is less than my 0.05. Let's actually adjust that real fast. It's approximately 0, which is definitely less than 5. All right, so, comma, there we go. What is the probability that x bar is greater than 12.09 fluid ounces? All right, so let's do the same thing again. So here's my mean of 12.07, my new standard deviation of 0.01, and this would be 12.08. 12.09 is about here. And I want to find the probability greater than that, so let's shade above this. All right, and that's what I want to know is, whoops, that's a 2. There we go, question mark. So I want to know what's that shaded probability. All right, so let's go back to my calculator. My minimum is 12.09. My maximum, I'm going to delete the 12, and so there we have it. That's our shaded region, and it's at 0.0228. Notice that is the value if you get 2 standard deviations or above, and you're not using the empirical rule. That's actually what you get, because that 12.09 is my is a z-score of 2 standard deviations above the mean. So the probability that x bar is greater than 12.09 is equal to 0.0228. All right, is it unusual to have a mean of 16 12 fluid ounce cans be greater than 12.09? Again, yes, because the probability that x bar is greater than 12.09 is 0.0228, which is less than 0.05. Now, if I would have said, what's the probability that I get a average of these 16 cans that's less than 12.09, is this surprising? Well, no, because almost 98% of your averages would be less than 12.09. So then in that case, that would not be surprising. But more than, yes. All right, without doing the calculations, consider the probability of finding a single can of Dr. Pepper to be greater than 12.09 fluid ounces. So just backtrack. So what if what we did up here where it's a single can and we have a standard deviation of 0.04, and I was to find where 12.09 is, which one of those is more likely? This mean of 16 and getting 12.09, or getting 12.09 when I'm just grabbing a single one, or do they have the same? Well, if I'm grabbing just a single one, graphically it would be about right here. That's where 12.09 would be. If I'm looking there and above, look how much greater area I'm shading in there. So typically, basically, whenever I increase sample size with these means, you're going to be decreasing the variability. So when I'm grabbing, I have a sample size of just 1, my data is much more spread out. So it's much easier to get some of those more higher numbers. But as you increase your sample size, it gets skinnier and skinnier. And so then where am I? Here I am. The likelihood that we get these numbers up here get smaller. So if I increase instead of 16, maybe I get I buy 10 different 12 packs of 120 Dr. Peppers. Then the likelihood of getting an average of 120 different Dr. Peppers being 12.09 might be pretty impossible feeling, kind of like the number we had earlier, because this going all over the place. Sorry, because this standard deviation would be a whole lot smaller. It would be 0.04 divided by basically almost 11. And so then this would be way, way, way over there. So the likelihood that we get it would be pretty small. When we increase our sample size, the variability decreases. So to answer the question, do you expect the probability of that single one to be more, less, or equal? We expect it to be more, in fact, and it will be. All right, just for fun, what are the lower and upper boundaries for X bar? The middle 70% of averages. All right, so let's do our middle percent dance after we get our graph drawn. 12.07. This is 0.01. 70%, now that is just above 68. So I'm pretty sure that's probably going to be, the z-scores at least would be 1.0 something, just barely above 1. So this is probably going to be about like 12 point, actually put question marks because I don't know, but it's probably going to be about 12.08 in a little bit, and then a little bit less than 12.06, but let's find out. All right, so here I've shaded it in. I've labeled this as 70%. There we go. So now we need to find what the unshaded regions are. And if you recall, we could do our middle percent dance. Remember, everything adds to 100%. If this is the middle 70%, that means collectively left in the wings is 100 minus 70, that's 30. So if I add both of those up together, I get 30 in both of those. How much do I get in just one of them? Well, that would be 15. So in just one, that's 15%, and the other one, that's 15%. So then I would find the area of 15% less and find that number, and then 85% and less for this upper one. So here less, that's going to be 85%, and here less, that's at 15. So over to the left on Desmos, I'm going to turn off the cumulative probability, and then I'm going to need to give it a letter. Let's use D for Dr. Pepper. Why not? So D equals, and then my second line, I'm going to do then D dot functions inverse CDF, and I'll put in 0.15. So it's, notice like I said it would be 12.06, but let's do a few more decimal places with it. 12.0596. So we get 12.0596. And then for 85, that's this upper boundary, this would be 12.0804. All right, so that means that the probability that X bar is in the middle 70%. Well, that is 12.0596 is less than X bar, which is less than 12.0804. And that equals 70%. All right, so basically two more or less points that I was making today. The first is that there's a difference between grabbing a single individual from a population and then when I'm grabbing multiple individuals and averaging. So make sure we are aware of that difference. And then secondly, the fact that what is unusual. If things are less than 5%, that starts entering our threshold of something's a little bit weird. That's every 1 out of 20. Somewhere around there, and then is when human intuition starts kicking in that you think something weird is happening. This is our that's that idea about that 5%. So if it's less than 5%, it's unusual, and we'll talk more about that in the coming lectures. So there you have it. Hope this helps you answer the questions that you need to do and finish up your tasks. Let me know if you have any questions, and I will see you next time.